that was the end of... Right, so now we move on to question 2. Half-time at the hockey match. The teams are waiting for the second half of the game. While waiting, the referee swings her whistle in a horizontal circle above her head. Each rotation takes 1.4 seconds. The metal whistle has a mass of 40.0 grams, and it is swung in a circle of radius 0.500 meters at a constant speed. So what do I note when I'm doing this to start with? Well, firstly, I note that these numbers have been given to 3 significant figures. I'm not sure that's super important, but I'm also seeing that this is clearly a circular motion question. Now, part A, what we've got to find is show that the speed of the whistle. So this is velocity equals distance over time. In circular motion, you have a constant speed. In part B, we've been asked to determine the horizontal forces on the whistle and explain why it continues to move in a circular motion. So this looks like using Fc equals mv squared over r to work out the force, and then giving an explanation of the direction and why it's the direction changing and not the speed. The third part of the question, the speed of the whistle is reduced to 1 meter per second. Determine the size of the new horizontal force on the whistle and explain the likely result of reducing the speed. So here we've got to again use our Fc equals mv squared over r to work out the new force. And then consider what effect this change in the force is going to have, maybe by thinking about what would happen if you swung a whistle around your head slower, at a slower speed. And I think most of us would have this kind of, if we imagine it, we'd realize that it slowly sinks down to a circle of a smaller radius. And we could consider vectors, using vectors to consider the forces on the whistle in the vertical kind of plane, an inward force, the horizontal force, and an upward force, the vertical force being the results of the tension in the string that's holding the whistle, with the upward force having to be balanced by gravity, or rather having to balance the force of gravity. So imagine if it's not moving at all, then the whistle is hanging straight down, but if it's swinging around really fast, then it's sticking straight out. Now we won't look at the part D yet because it's on the next page, so we'll first solve parts A, B and C and go from there. So question 2A. Well, let's see, we've got velocity equals distance over time. We need to know the distance. In this case, the distance is the circumference of the circle. The circumference of a circle is given by 2 pi r. So d equals 2 pi r, 2 times 3.14 times 0.500, which is, of course, 3.14 meters. The time is 1.40 seconds, so v equals d over t. We solve that, we get v equals 2.24 meters per second. And I've written... and I've should be given to 3 significant figures, in fact. Okay, part B. So the centripetal force for an object in circular motion is given by Fc equals mv squared over r. The centripetal force, of course, is the force that pulls toward the center of the curve, or the center of the center of curvature of its path. So Fc equals mv squared over r. We've been given v as 2.24. In fact, we've calculated it as well. The mass is 40.0 grams, which we have to convert to 0.040 kilograms. And the radius is given as 0.500 meters. So we substitute that into the equation, F equals mv squared over r, and we get 0.40 newtons. And I've given that to 2 significant figures. I actually think I should have probably rounded that only to 3 significant figures, so that is perhaps a mistake on my part, but it might of course be accurate. Part B. Continuing part B, we still need an explanation for why this leads to circular motion at a constant speed. So the force is provided by the tension in the string. This is perpendicular to the horizontal velocity all the time, which means that this force only changes the direction of the velocity, not the size of the velocity. The nature of the arrangement of the string means that the force remains perpendicular to the velocity throughout. Alright, part C. We've been asked to determine the size of the new horizontal force on the whistle. So we just run through the same equation again. It seems unusual to give an exam question where they'll make you do that, so I'm not sure what they're doing there. And this time we get Fc equals, the centripetal force equals 0.080 newtons to 3 significant figures. The centripetal force has reduced, which means that the relative effect of gravity will be higher compared to the horizontal force, and the whistle will drop to a lower, smaller circle where these forces are back in balance. Now you can actually, you could work this out either using, it would be possible to work this out using a vector diagram. They haven't asked you to do that, I don't think, and you could even go further with that and look at torque and equilibrium, but again I don't think they've asked you to do that. So a qualitative answer. Right, now we move on to part 2D. So part 2D, let's see, we've got the team waiting on the sideline. The 2 players sit on the bench as shown. We've got a whole lot of data about the masses of the people and the distances, and we've been asked to draw labelled arrows showing all the forces acting on the bench. We've also been asked to determine torques around point B, or by determining torques around point B, calculate the support forces at each end of the bench. So this is clearly a torque and equilibrium question. So the starting point here is to draw labelled arrows showing the forces acting on the bench. I don't think they've asked for the labelled arrows to include the actual forces, so I'm just going to label them rather than give the calculations, and that's partly because they haven't provided space for the calculations there in part 1. So what have I got? I've got FA, the support force at A and the support force at B both upward, and then we've got the weight of the bench, the weight of each person all downward. Alright, now determining the torques about point B to calculate the support force at each end of the bench. And what assumptions have we made? Well, let's start with the assumptions. So the first assumption we've got is that for equilibrium, the clockwise torque equals the anti-clockwise torque, and that the net force is 0. I guess the actual assumption for that is that the bench is not moving or not accelerating. I think the main assumption they really want you to make is that the bench is uniform, so that the mass of the bench can be considered as applying at the centre of the bench, the centre of the length of the bench. That's what I think is the key assumption. Alright, now torques in I'm going to work out the torques in the anti-clockwise direction first, because that's most of them. So this is torques about point B, so torques in the anti-clockwise direction. Force of the bench the weight force of the bench, so that's and then that's at 0.75 meters, so halfway along the bench. And then we've got the weight forces of the two people, which are acting at 0.6 meters and 0.25 meters. So when you go to work something like this out, you're looking at two equations for each of these torques. The first equation is obviously the torque equals force times distance, but to get the force you need to use mass times gravity. And then we substitute these numbers into our equation, so we get that the three torques, 60 times 9.8 times 0.60, 60 times 9.8 times 0.25, and 10 times 9.8 times 0.75. We work each of those out, add them together, and get 573.3 Newton meters. Now, I'm not going to round that at this point, even though we've got the players' masses, where some of these things might only be to two significant figures. We're not going to round them because we want to carry through as much accuracy as possible to later in the question. Alright, now the torque, for equilibrium, the torque in the anti-clockwise direction equals the torque in the clockwise direction. Now about point B, the only torque in the clockwise direction is from the support force at A, and that acts at 1.5 meters from the support B. So we can now substitute in the clockwise torque equals the anti-clockwise torque, so that's 573.3 on the left-hand side of the equation, equals the support force at A times 1.50. So the support force at A equals, in the end, 382.2 newtons. Now I'm going to keep that written down, but I'm going to round it also to 380 newtons to two significant figures for the answer. The forces at now, to find, so that's given us the support force at A. We now need the support force at B. To do that, we're going to use equilibrium in terms of forces. So the sum of the upward forces equals the sum of the downward forces. And we substitute in and rearrange a little bit, and we come up with 800. Let's have a look. We come up with 891.8 newtons, which we can round to 890 newtons to two significant figures. Right, that was part 2D. So quite a different context to the first two parts of question 2.